Alright guys, today we are looking at inverse matrices and solving systems. Our objectives are to determine whether two matrices are multiplicative inverses, to determine whether a matrix has a multiplicative inverse, to find the inverse of a matrix, and lastly, to solve a system of equations using inverse matrices. So let me get started by reminding us of something. How is it that you would solve this equation for x? This is one of those simple one-step equations from Algebra 1, but perhaps it's the terminology that we've forgotten. We would multiply each side by the multiplicative inverse of a. The multiplicative inverse of a is 1 over a. When you multiply that left side, the multiplicative inverse and a, this will equal 1. That number is called the multiplicative identity. So you'd only have one x, which is what we were looking for. X is now isolated, and you could write that as x equals c times a. So those two terms, multiplicative inverse and multiplicative identity, are going to be seen in this section in reference with matrices. So let's get started with a few definitions. The identity matrix, the multiplicative identity matrix, has elements that are all 0 other than those on the main diagonal. And on the main diagonal, they're going to be 1. If you had a 2 by 2 matrix, it would look like this. This would be the identity matrix. On the main diagonal, going from the top left to the bottom right, you would have the elements 1, and in the other positions, 0. A 3 by 3 matrix would look like this. So on that main diagonal from the top left to the bottom right, you have 1s, but everywhere else are 0s. These are multiplicative inverse matrices. Of course, we could make them much larger, but we're not going to be working with those in this section. Now, the multiplicative inverse matrix of A is A inverse. And when you multiply those together, you'll get the multiplicative identity matrix, which is that I matrix that we were just looking at. So multiplying those together gives you the I matrix, or like in real numbers, just 1. So let's look at something here. We can determine if two matrices are inverses by finding their product. So we would set these up, and you can multiply them because you have a 2 by 2 times a 2 by 2, which will give you a 2 by 2 matrix, filling in with 2 rows and 2 columns. And I like to circle those, divide them off, so that it's easier to multiply. It just helps me to organize. So we're going to find those elements that should be in the product and see if they give us our identity. So let's get started. For C1, it'd be 4 times 3 halves plus -2 times 5 halves, which gives you -1. Now moving over, if you're trying to find C2, it'd be 4 times -1 and -2 times -2, which gives you, well, that would be -4 plus 4, giving you 0. Then C3, that's going to be 5. Now I'm working in my second column, first row. That would be 5 times 3 halves and negative 3 times 5 halves. And that gives us 0. And lastly, multiplying second row, second column will give me that final position, and that product, those two products when added, is 1. So if I plugged that in to the matrix into the appropriate positions, that would give me my identity matrix, which means these two matrices are in fact inverses because their product is the identity. That is our definition. So, what if you take the determinant of a matrix and it's 0? That is going to be an indicator that your multiplicative inverse will not exist. So now you're probably wondering, well, how do I find my multiplicative inverse? The multiplicative inverse of a matrix A is going to be 1 over the determinant of A. Now I think you might see why the determinant cannot be 0, because that would be dividing by 0, which is undefined. So that's why we had that stipulation. Then what happens inside that matrix? Well, the D and the A positions get flip-flopped. And B and C, those values would stay in the same place, but we would make them the opposite. So again, you're going to have 1 divided by the determinant of A. And if the determinant of A was 0, then you wouldn't have an inverse. But if it was something other than 0, you could go ahead and find inside that matrix you would need to switch A and D, those two values, and take B and C and make them opposites. Let's do this together because that might seem a little strange just looking at the formula. Here's our matrix A, and we're going to find the inverse of it. Well, the first thing I'd want to do is find the determinant of A. That would be 1 times negative 4 minus negative 2 times 5, which will give us 6. Okay, since the determinant of A is a real number, we can continue on with this process. If it would have been 0, we would have just stopped. So now I'm going to plug that in to the denominator of that scalar on the outside. So we're going to have to multiply 1/6 into our determinant. You'll notice, into our matrix, You'll notice that in that matrix, the values have kind of been changed. If you look at the original, look what's happened. We've switched 1 and negative 4. Their positions have been flip-flopped. 5 and 2 stayed in the same place, but 5 was originally positive, the B position. Now it is the opposite, and it is negative. The C position, originally negative 2, is now a positive 2. We made it the opposite. Okay, so inside is good. Now we just need to multiply it by that scalar. When we do that, we'll have negative 4/6, negative 5/6, a positive 2/6, and a positive 1/6. And we can simplify that down to a negative 2/3, negative 5/6, a 1/3, and 1/6. If you took this matrix and multiplied it by A, you would get the identity matrix. Let's try one more of these, and then I'll show you why it's important to be able to find this inverse matrix. Here's our second one. We're now working with matrix B, and the values there are negative 3, 2, 6, and negative 4. Those are the elements in the original matrix. So again, to find the inverse, we need to find the determinant. That means we're going to multiply -3 times -4, that's on the major diagonal, and subtract 6 times 2. But that gives us 0. If I tried to plug that in, I'd be putting a 0 in the denominator, which is undefined. So at this point, we can only say that the inverse of b does not exist because the determinant of b is 0. So we go through this process of finding the inverse when you see problems like this. We're trying to solve for x, which means we would need to eliminate that matrix on the left side. And to be able to eliminate that matrix on the left side, we need to find the inverse of that matrix, which you would call A. So let's begin. To find the inverse, we need to find the determinant. That's going to be, if you multiplied 6 and 13, that gives 6 and 3, that gives you 18, minus 2 times 8, which is 16. The difference there is 2. That value, look there, it is on the outside of the matrix in the scalar's denominator. It's always 1 over that determinant. And we've switched up the values inside of the matrix. The 6 and 3 have been flipped. The 8 and 2 have been made opposite. After you have that, we move on to step 2. You'd want to distribute that 1/2 into the matrix. The scalar needs to be multiplied in. Then you'd multiply each side of the equation on the left-hand side by your inverse matrix. You always have to multiply it in that same position. So always on the left-hand side. And because we're working with the inverse of A times A, that means that that product is going to be the identity matrix. So we've already started to simplify, but that's going to be our next step because notice on the right-hand side we have a product that we need to find. So our third step is to simplify. X, the value that we're looking for, the matrix that we're trying to find, is going to be the product of those two matrices, which, yeah, we can multiply. You can check their dimensions. We can set them up in that fashion. I have to be able to multiply this, and I encourage you to as well. And the result is going to be a 2 by 1 matrix. We multiply 3/2 times -2, and that's going to be -3. -3, you would add to that in the next, but it would be -4 times 0, which is going to be 0. So we're just going to have -3 for that first value. Now let's move down. You'd be multiplying -1 times -2, which is a +2. If you tried to add the next thing, it would be 0 because 0 times 3 is 0. So there we have it. The matrix that we were trying to find, the X matrix, is going to be -3, 2. Those two elements there. So there you have it. Now you know how to find the identity matrix for any matrix, and you know how to check, and now with it you can solve these simple matrix equations. And that's all.